Linked lists are the foundation of dynamic data structures. This presentation provides an introduction to linked lists. A linked list is a linear data structure where elements are stored in nodes. Each node contains data and a reference to the next node. Nodes are connected through pointers, not by physical placement in memory. The first node is called the head, and the last node points to null, indicating the end of the list. Unlike arrays, linked lists do not require contiguous memory locations, offering flexibility in memory allocation. Let's delve into the key components of a linked list. The node is the basic unit, containing both data and a reference, often called next. The head is a pointer to the first node in the list. Some linked list implementations also maintain a tail, which is a pointer to the last node for efficient operations at the end of the list. The next reference within each node points to the succeeding node in the sequence, and importantly, the null reference in the last node signifies the end of the list. Understanding these components is crucial for manipulating and traversing linked lists effectively. Linked lists come in several flavors, each with its unique characteristics. First, we have the singly linked list where each node points only to the next node in the sequence. This is the simplest form, allowing traversal in one direction. Then there's the doubly linked list, where each node contains pointers to both the next and the previous nodes. This bidirectional structure allows for efficient traversal in both directions. Lastly, we have the circular linked list, in which the last node points back to the first node, forming a circle. This type is useful in applications where cyclical access is required. Choosing the right type depends on the specific needs of your data structure. There are several compelling reasons to opt for linked lists in your data structures. Linked lists offer dynamic size, meaning they can grow or shrink during runtime, adapting to changing data needs. They provide efficient insertion and deletion operations, achieving order of one-time complexity when the position is known, as elements don't need to be shifted. Linked lists optimize memory utilization by allocating memory as needed, avoiding wastage. Their implementation flexibility allows easy adaptation to various scenarios, making them a versatile choice. Linked lists manage memory by allocating it in non-contiguous blocks, which contrasts with arrays that require contiguous memory allocation. Let's compare linked lists and arrays across several key features. Memory allocation in linked lists is dynamic, occurring at runtime, whereas arrays have static allocation, fixed at creation. Element access in linked lists takes order of n time due to sequential traversal, while arrays offer order of 1 time, providing direct access through indices. Insertion and deletion in linked lists can be done in order of 1 time, when the position is known. Arrays take order of n time as it may require shifting elements. In terms of memory usage, linked lists require extra memory for pointers, while arrays are memory efficient with no overhead. Linked lists use non-contiguous memory blocks, whereas arrays require a contiguous block. Finally, linked lists support forward traversal or bidirectional traversal, while arrays allow traversal in any direction. Linked lists find applications in a wide array of computing scenarios. They serve as building blocks for more complex data structures, such as stacks, queues, hash tables for collision resolution, and adjacency lists for representing graphs. In navigation systems, linked lists are used to track browsing history, maintain undo-redo operations, and create playlists in media players. Operating systems employ linked lists for managing free memory blocks, allocating and deallocating resources, and scheduling processes. Moreover, linked lists are fundamental in real-world systems like image viewers for slideshow functionality, music players for playlists and queues, and social media feeds for infinite scrolling. Let's explore a basic implementation of a linked list in Python. First, we define a node class which contains the data and a reference to the next node, initializing the next reference to none. Next, we create a linked list class which maintains a head pointer, initially set to none for an empty list. Within the linked list class, we define an append function to add a new node at the end of the list. If the list is empty, the new node becomes the head. Otherwise, we traverse to the last node and add the new node to the end of the list. Key implementation points involve managing node structure, maintaining the head pointer, and implementing operations such as append, insert, and delete to manipulate the list. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.